Chemistry Chapter 1, Periodic Table, Part 2, the periodic trends and properties. The first property we are going to study is atomic size. Definitions have already been marked earlier. So it is measured in angstrom. Angstrom spelling corrected. 1 angstrom is equal to 10 raised to minus 10 meters. Now, if there is a hydrogen molecule or any molecule, the internuclear distance is called the bond length. And this bond length helps us to determine the atomic radius. You can see the atomic radius is half of the bond length if you imagine the two atoms to be close to each other. Now, there are two factors which affect the atomic size: number of shells and nuclear charge. If you talk about number of shells across a period from left to right, the number of shells remains the same. For example, period 2 have 2 shells, so that won't affect the atomic size. But the nuclear charge increases. What is nuclear charge? Mark the definition. It is the positive charge on the nucleus. That is the number of protons. So simply speaking, it is the atomic number. Lithium's nuclear charge, let's call it 3, 4, 5, 6, 7, 8, 9, 10. Now, more the number of protons, more is the nuclear pull on that last shell, which is negatively charged due to electrons. So from left to right, since the nuclear charge increases, atomic size decreases. That is why in period number 2, lithium is the biggest atom and fluorine is the smallest atom. Something like this. Mark these, give reasons. But the neon has even more nuclear charge compared to fluorine. Yet it is not the smallest atom because it is a stable atom. Its outermost shell is complete, due to which some force of repulsion comes into effect. So it's an exceptional case. Its size is somewhere in between these elements. So noble gases are not the smallest atom in the respective periods. However, in the entire periodic table, the smallest atom is that of helium. Yes, helium is also a stable atom, but considering all factors, helium turns out to be the smallest atom. Just one shell and 2 protons attracting the last shell, smaller than even hydrogen. The largest atom shall be francium because it has 7 shells and its nuclear charge is the least in period number 7. Neon, mark the GR, cancel seen and write much. Now, if you compare 2 particles, one is an atom and one is a cation, which one will be smaller? Well, it has to be the cation because if you compare, say, sodium atom and sodium cation, sodium atom is 2,8,1, sodium cation is 2,8, so it has only 2 shells. This has 3 shells, so definitely this will be smaller. Remember, cations are always smaller. Mark it as a GR. But the answer, let me give you an easy point for the answer. Also, sodium cation has 2 shells while sodium atom has 3 shells. But let me give you another example. Take magnesium atom and magnesium cation, but singly ionized, not doubly ionized yet. So this is 2,8,2 and 2,8,1. So both of them have same number of shells, 3 shells. Then how do you decide which one is smaller? Well, the second factor is nuclear charge. Guess which one has a smaller nuclear charge? Well, actually both of them have the same nuclear charge, 12 and 12. Nuclear charge means number of protons. That doesn't change. It remains the same. Let's talk about nuclear pull. Here, the 12 protons have to attract the 2 valence electrons, whereas here the same 12 protons have to attract just 1 valence electron. So it will be easier to pull it closer to the nucleus. So effectively, this cation is smaller than the atom. On the other hand, anions are bigger than parent atoms. 2,8,7 and 2,8,8. Well, 17 protons have to pull 7 electrons, but here the same 17 protons have to pull 8 valence electrons. That is more difficult. Anion will be bigger than the parent atom, even though the number of shells are same and even the nuclear charge is same, but nuclear pull can be different in this case. So, notice these isoelectronic ions, which have the same electronic configuration, 2,8, 2,8, 2,8, 2,8 and 2,8. So they have the same number of shells. And yet the cations are the smallest and the anions are the biggest here because of change in nuclear charge. Magnesium has the highest nuclear charge of 12, so the highest nuclear pull on those valence 8 electrons here. And oxide has nuclear charge 8, so only 8 protons attracting the last shell of 8 electrons, the least nuclear pull. So this is the smallest ion and this is the largest particle. And please write this as well, and an ion is larger than the parent atom. So mark these 2 points together as a GR, neon GR, cation GR. Values are not to be learned in this chapter at all. And mark this entire section 4 as a single GR. Again, don't learn the values. Now, down the group, atomic size increases, which is obvious because number of shells are increasing. Cesium has 6 shells and lithium has only 2 shells. But the second factor was about nuclear charge. Lithium has nuclear charge of 3, 11, 19. So by that logic, atomic size should decrease. So there's a contradiction between the 2 factors. However, number of shells is the dominating factor. So overall, atomic size will definitely increase. By the way, the truth is that even though the nuclear charge is increasing, the effective nuclear pull reaching the last shell is decreasing. Because there are so many shells in between, there's a shielding effect. Now the next property trend is for IP, ionization potential. If you remove the first electron from magnesium and make it Mg1 plus, it is called the first IP. And then if you remove one more electron from the last shell, it is called Mg2 plus. And that energy is called second IP. Second IP will be more than the first IP because after the one electron is gone, the nuclear pull is concentrated on that remaining one electron. These energies are very small. They are measured in a small quantity called a unit called electron volt. 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule, which you will study this in physics. But the SI unit is joule per mole. Mention that. The two factors which affect IP are atomic size and nuclear charge. Give reasons. Let's understand it with the help of the example of period 2. From left to right, atomic size decreases. That means the last shell is closer to the nucleus in fluorine and farther to the nucleus in lithium. Now, when the valence electrons are closer to the nucleus, it is more difficult to remove them from their shell. More energy will be required. Whereas for big atoms, if the valence electrons are far away from the nucleus, it is easy for them to escape. Less energy is required. So metals always have a low IP and non-metals have a high IP. So IP increases from left to right because atomic size decreases and also because nuclear charge increases. Here we have 3 protons attracting the valence electrons and here we have 9 protons attracting the valence electrons. So clearly here it will be more difficult to remove the electron from the last shell. More energy will be required, so IP increases from left to right. In fact, IP is highest for neon in this period. Because asking a noble gas, a stable atom, to lose an electron will require a tremendous amount of energy. Yeah, even for halogen who want to gain electron, if you want them to lose an electron, be ready to spend a lot of energy. But lithium, it's a metal. It would happily, readily lose an electron. Less energy is required, less IP. So combine these two factors into a GR. In exam, if some application-based questions are asked, like why does oxygen have a higher IP than boron, then you have to frame using these keywords. You can say that from left to right, IP increases because atomic size decreases and nuclear charge increases. Oxygen is to the right of boron. Hence, in the entire periodic table, helium has the highest IP and cesium has the lowest IP. And mark this as a GR, write the word readily. And mark entire section 4 as a GR. Again, as you go down the group, atomic size is increasing, so IP decreases down the group. It is easier for cesium to lose that last electron so far away from the nucleus, a little bit of energy, and it would readily lose the electron. But the second factor is contradictory. The nuclear charge is increasing down the group, so the IP should also increase. However, atomic size, atomic radii is the dominating factor, so overall we say that IP decreases down the group. By the way, the effective nuclear pull is actually decreasing down the group, even the nuclear charge is increasing, due to the shielding effect of the inner electron shells. Next property is electron affinity. Here the energy is calculated with the unit electron volt and we put a negative sign because in this case energy is liberated. We don't give it the energy. That's for IP. The factors are same, atomic size and nuclear charge. So if you again look at period number 2, from left to right, atomic size decreases. So fluorine with the valence shell close to the nucleus would readily accept the electron and would release more energy. It'd be very happy. Lithium, it's a bigger atom, so it won't accept electrons so readily. It's a metal, it wants to lose electrons. So it won't be that happy if you force it to gain an electron. So electron affinity, like IP, increases from left to right. Values are not important. So many exceptions. Chemistry is full of exceptions. Their reasons will be taught in higher standards. Combine this into a single GR. So again in period 2, highest electron affinity is for fluorine, but the lowest is not for lithium. It's for neon, because there is 0 electron affinity for neon. There is absolutely no way it will ever accept an electron. So mark that as a GR. And inert gas is also GR. Electron affinity is highest for halogens and least for, cancel alkali metals and write inert gases. Now again down the group, if you talk about atomic size, it increases. So let's talk about halogens. So iodine won't be as happy to receive that electron on that 5th shell as fluorine would be to receive the electron. Small atoms readily gain electrons. Large atoms don't gain electrons so readily. So electron affinity decreases down the group. Less energy is released down the group. But if you talk about nuclear charge, as that is increasing, electron affinity should increase. So again, there is a contradiction. And again, I would say that atomic radii or size is the dominating factor. So overall, electron affinity decreases down the group, just like IP does. However, there is one exception. You would expect fluorine to have the highest electron affinity in the entire periodic table and among the halogens. But no, that crown goes to chlorine. You see, theoretically, yeah, fluorine is smaller. It should more readily accept the electron. But the fact is that the atomic size is so small. When you try to add an 8th electron in the second shell, where already there are 7 electrons in such a small space, there is some repulsion. So it doesn't accept the electron as readily as chlorine does, which has more space in its third shell. So chlorine has the highest electron affinity. So write it. Electronegativity is similar to electron affinity, but it's a tendency. There's no unit to measure it, although there is a scale from 0 to 4. So the highest electronegativity is for fluorine. Yeah, no exceptions in this case. If the electronegativity difference is large, like more than 1.7, an ionic bond is created. The metal will lose electron and the non-metal will gain it. Otherwise, if the difference is quite small, they will share the electron, forming a covalent bond, which can be polar or non-polar, which you will study in chapter 2. Same two factors, atomic size and nuclear charge, mark the GRs. So from left to right, this is period 3, by the way. From left to right, atomic size decreases. Chlorine has the smallest atomic size here. So it will be greedier for the shared pair of electrons. High electronegativity of 3. Alkali metals have low electronegativity. In fact, cesium has the least electronegativity. Noble gases, it's nil, not even 0. We can't even talk about them because electronegativity is the tendency to attract the shared pair of electrons. But noble gases never share electrons with anybody. So we can't talk about it. Combine the two factors into a single GR. Some fun facts here. Section 4 is entirely a give reason. Same 3 points. Same contradiction, but atomic radii is dominating. So overall, electronegativity decreases down the group and it increases from left to right, just like IP and EA. And then the 5th property, metallic and non-metallic property. Metallic atoms are on the left of the periodic table. Why? Because in any period, they have the largest atomic size and the least IP. So they tend to lose electrons more readily. GR. Similarly, non-metallic atoms, GR, they are always on the right of the periodic table because in a period, they have the smallest atomic radii, the highest IP. In fact, for noble gases also it's highest, but noble gases are not called metals or non-metals. So non-metals, like halogens, they gain electrons very readily. Study about reactivity as well. Now combine these 2 points into a single GR. From left to right, metallic character decreases and non-metallic character increases because atomic radius is decreasing and IP is increasing. So it is becoming more and more difficult to lose electrons and more easier to gain electrons. We're talking till chlorine, okay? We're not talking about noble gases. Down the group, again, same two factors. Atomic size is increasing and IP is decreasing. So it becomes easier, more and more easier to lose electrons. So metallic character is increasing and non-metallic character is decreasing because it becomes more difficult to gain electrons. No contradiction here, and mark this section as a separate GR. Now, physical properties are cancelled. Chemical properties, we have already studied from left to right. Basic properties decrease and acidic properties increase. Cancel hydrides. Now, this is the definition of stable elements. Cancel light metals. And this is the definition of unstable elements. Cancel heavy metals. Elements with a N upon P ratio, neutron upon proton ratio, above 1.5, meaning they have many more neutrons compared to protons, are highly radioactive, unstable elements. Examples are heavy metals and uranium. These reference values are cancelled, but you may want to refer to electronegativity values. Hi students, this is AJ sir. If you found this video useful, press the like button. Also, if you'd like to enroll for my test series or online lectures, email me or message me on Instagram. Check my description for more information.